Great. Thank you very much. I'll repeat what I said a few minutes ago, which is that I'm coming from a particle physics background, and this work is bringing me more and more into the realm of condensed matter physics, more and more into essentially your realm, the realm of the people, of all of you who have joined this. So I come here kind of with a humble mindset. I'm sure that many of you know the physics of helium-4 much better than I do. I'm essentially stealing condensed matter physics and applying it to a particle physics problem. I'm trying to apply some of the things that you all study for academic reasons, just apply them in a surprisingly practical situation to solve a challenge in particle physics. So yeah, please forgive me if I say something that you disagree with, and don't be shy to correct me and teach me things. First, I'll explain the name. So HeRALD stands for helium roton apparatus for low mass dark matter. Alternatively, light dark matter, but it gets confusing to say light and dark next to each other. So the particle physics context, just briefly here. So we believe that we're surrounded by this bath of dark matter particles. They're moving at galactic velocities, so roughly hundreds of kilometers per second scale relative to us. The signature that we're looking for is an interaction between that particle and an atom. So an atom will recoil at some energy dependent on the mass of the dark matter particle, and we have nearly no constraints on that dark matter particle mass. So for many decades, much of the field has been focused on the electroweak mass scale. This was partly due to supersymmetry models, partly just a general theory prior that we expect new physics at that scale. So if the dark matter particle is at this GeV to TeV scale, then the recoiling atom would have an energy something like a KeV energy scale. Over the past few years, decade or so, there's a new trend. People are gradually realizing that we need to be looking everywhere we can for dark matter. We need to test all models that are consistent with cosmology. One such model is just to drop the mass of the thing that we've been looking for decades and look at the mass range of 1 keV to MeV scale, maybe 10 or 100 MeV. The signal there is going to be the same thing. It's going to be a recoiling atom, but the energy will be dropped accordingly. So now it will be in the sub-eV regime. And that is a big challenge. We don't have good detectors. We don't have technologies that can find sub-eV nuclear recoils in a large target mass, in a large collection of many atoms. So that's where this whole helium project comes in. If we had a helium-4 target material, and we were looking for recoils of helium-4 atoms in that material, this is a kind of the search space. We have dark matter mass here in MeV units. We have nucleon scattering cross-section here, normalized to the per nucleon state. You see these numbers are small, 10 to the minus 40 centimeters squared cross-section scales. This corner is high cross-section and high mass. That's where we can probe things with KeV recoil energies. If we had a helium detector with a 20 EV threshold, and say 10 grams for a year, then we would be probing significantly new phase space in a region that's pretty easy to defend from cosmological arguments. And then if we pushed that threshold lower and lower, we would push lower and lower in our mass threshold in this axis and probe more and more of these models that are favored by simple cosmology. So the 2 points on this slide, the experiment of small mass is already useful. And the key is you need a tens of EV thresholds or lower in order to start probing new regimes. And we don't need large masses. We don't need extreme radio purity. We can do this experiment in a university lab above ground. It's kind of a tabletop size. You need a dilution fridge, and everything fits inside of it. So this might sound quite familiar to some of you. So this is another thing that I'm sheepish about, which is that essentially we are stealing everything from HeRALD R&D, which was this other project that used a very similar signal from helium-4. The only difference was that they were aiming towards a much grander scope. So they were aiming for a 10-ton experiment. They were looking at higher energies, so keV scale, electron scattering from solar neutrinos. And what we're doing is actually much easier. So now that this low mass dark matter model is interesting to a lot of theorists and experimentalists, it's something that is newly interesting for us experimentalists to look for. We're trying to push the threshold lower to these sub-EV thresholds. And instead of 10 tons, we can make an experiment that's 10 grams. So it makes our lives, this is a very achievable goal in my mind. In a small number of years, we will be setting limits using this technique. The primary signal channel here is quantum evaporation. So probably most of you are well aware, but the typical, well, one thing is you'll notice I'm always using these EV units, and probably most of you are more familiar or more fluent in the language of temperature, Kelvin units. So maybe that's the main point, is just for you to get used to my units here. So the typical quasi-particle energy in the helium-4 is roughly 1 millieV. And the binding energy of the atoms at the liquid surface is roughly 0.6 millieV. So we get this process where one quasi-particle can liberate one atom. And so we call it quantum evaporation. It helps a lot on getting grant money to have that word quantum in the title of all our proposals. So maybe to emphasize, the target material here is isotopically pure, so that we have ballistic propagation of the quasi-particles. There's no scattering off helium-3. And it's below 100 milliK, so that we don't have any thermal phonons in that can cause a secondary type of scattering of the quasi-particles. So these are as ballistic as possible to make the signal as simple as possible. And then we detect those liberated atoms up here on a calorimeter, a sensor that just senses energy. And one of the advantages of an energy-based sensor is these atoms actually fall into a potential well. They're attracted to the calorimeter with a van der Waals potential. And the energy of that van der Waals potential is 10 or tens of millieV. So it's significantly greater than the initial quasi-particle energy. So it's a gain mechanism. We start with an excitation, and that excitation rolls down a hill so that we see more energy than we started with when we do the sensing. And that's one of these huge advantages. There are not many modes where you're essentially just sensing kinetic energy, a recoiling atom, where you have a gain mechanism between that recoiling atom and your sensor. So that's a huge advantage over anything that's not using helium-4. Another advantage is that our signals are always going to be shared between multiple channels. The evaporation is pretty diffuse. It has a wide range of angular dispersion. So we have shared signals from helium-4. Any backgrounds that's specific to the sensor are going to be in one sensor at a time. So we have this separation between the complicated sensor, which might have its own backgrounds from stress and clamps, etc., and this huge stress-free three-dimensional volume that should have very low backgrounds at low energies. We don't have any kind of stress fractures or slippage or clamps. We expect EV scale backgrounds from helium-4 spontaneously relaxing in some way to be low in rate compared to the silicon or the metals of the sensors themselves. So these are two really strong sales arguments in favor of this technology. There's a secondary signal. I don't think of the atomic excitations as the primary signal because we're looking for sub-EV signals. And these atomic signals are only produced for recoils above this 20 EV scale. Quasi-particles have an increasing fraction of the recoil energy, and then below 20 EV, it's 100% of the recoil. But still, we need to pay attention to them. Above 20 EV, they do contribute significantly. Like 20 or 30% of the energy goes into singlets. Above 10K EV, a lot of the energy goes into the triplets. So picture all of these dimers here at the recoil site, and then what happens to them? Will they cause backgrounds for us? Will they help us discriminate backgrounds from signals, etc.? So the singlet dimers are a very simple story. They have a prompt decay, and we see them as scintillation photons. Essentially, immediately upon the energy deposition in the helium, we see photons arrive at the calorimeter. The triplet dimers are interesting. So they propagate in the bulk superfluid. They have a very long lifetime. So they actually reach the walls or the liquid surface before they decay, predominantly. And then they undergo quench or decay processes at the surface. So the physics of that interface dominates how these triplets decay and release their energy. At the helium-4 to metal interfaces, like along the walls of your bucket, they exchange their excited electron with the surface. That surface finds a way for that electron to fall in energy. At the vacuum interface, they're still very long-lived, but we've kind of collapsed the 3D volume onto a 2D volume where the triplets have a higher probability of finding another triplet. So we expect diffusion of those triplets on the liquid surface, and then we expect the decays there to be dominated by triplet quenching, which would be density dependent, which should fall as 1/T. So there's kind of three different behaviors here. There's the singlets that arrive promptly. There's triplets that arrive at the walls, and there's triplets that arrive at the liquid surface. Maybe I'll just repeat, for a particle physics experiment, the triplets are a very scary attribute of helium because they're so long-lived. You can imagine a lot of pileup. So one event, if it has a very long-lived excitation, will run into the next event, and you won't have any quiet window between your. In order to do any of this work, we have to stop the helium-4 film from creeping along the wall from the target helium and reaching the sensor. The sensor needs to be dry in order to sense the arrival of the evaporation atoms, or at least in order to have that gain mechanism. That is really advantageous. And then that sensor also needs to be very cold. So in general, for this type of calorimetry, the sensor threshold depends on T cubed. So we need a method to stop the film that does not apply any heat, or at least minimal heat, down the support structure to the sensor itself. That's a big challenge. Heron and other projects have used a film burner for this. So the film creeps up the wall, it reaches a hot region where it evaporates completely and stops continuing to flow. The cons of that, one is it applies really significant heat loads where that evaporated population of atoms condenses. So you need to deal with that high heat load and pull that heat away. There will be some leakage of that heat down to the sensor itself. And then additionally, you have a lot of liberated atoms here, which you need to make sure none of them diffuse in a gas mode down to the sensor. So you'll have some unavoidable heat load and you'll have some level of gas leakage to the sensor. So we have been looking for alternatives. One alternative is a knife edge. So when the superfluid film creeps over an atomically sharp corner, it thins the film with a van der Waals force down to the single atom layer where it's no longer superfluid, no longer flows over that edge. So the pros there is that there's no heat load and there's also no evaporation. So it just stops the film without liberating any atoms into the vacuum. The cons, though, it requires a really extremely small radius on that knife. So this has been demonstrated at higher temperatures, but at temperatures where we are, sub 100 milliK, we need a radius that's sub 10 nanometers. So that's just a very difficult technical challenge to have a sub 10 nanometer knife that goes around a macroscopic region. We've tried, we've done pretty well, but I think I think that road is very long to try to achieve this goal. Okay, so then what we've settled on is using cesium. So cesium, here's a photo from other people's work where you can see a drop of helium-4 sitting on an unoxidized cesium layer. So that's really unusual to see a drop of helium-4 sit like that. It is not wetting the cesium, it's not spreading out. And cesium is one of the very few materials with this unusual wetting behavior. So, you know, helium obviously wants to cover everything, but it does not want to cover cesium. So if you put unoxidized cesium here, you can produce a barrier for the film flow. Just like the knife edge, this applies no heat, it's just passive. And it does not introduce any evaporation. It's just a boundary with no high energy input. However, this is really, really challenging. So the cesium surface must be unoxidized. So that means we have to deposit it in situ in the cell after pumping it down. And it has to be done each time. Each time we open the cell, we destroy the cesium surface. Depositing that cesium requires a high temperature, something like 800 degrees. And so that means we need to supply high current leads to the mixing chamber stage, something like 7 amps. And the cesium itself has a relatively high vapor pressure at room temperature. So that means the cesium will migrate and poison the detector. So in order to keep the cesium where we want it, we have to deposit it relatively cold, definitely below 100 Kelvin. And we have to kind of fix it chemically while warming up to keep it from turning into a gas at room temperature before we open the cell. So this was a huge ordeal, a huge challenge. I'm glad that we finally have solved all these practical challenges and we're looking at beautiful data. Here's just a cross-section view of the cell that we have here at University of Massachusetts. So we have the helium-4 target region. We have a bunch of copper plates here that are mostly just to provide shape to the target region, but they also reduce gamma backgrounds. Here's the sensor in yellow and its copper support structure. This is all kept film-free because we have these cesium dispensers that have deposited cesium on that support structure right here. Just a little bit of show and tell. Here's what that cell looks like in real life and a more realistic CAD. Here's what the cesium dispensers look like and the bulky leads to carry the many amps. So these are commercial products. You can buy them from SEAS. They're used to make LEDs and other complicated light emitting objects. We plated some gold here, trying to make the surface as inert as possible to make sure that the cesium does not get lost before it's used, to make sure it's not diffusing into the material or chemically bonded. And here's a view of that target region right here. There's a pocket around it where the calorimeter sits. Let me tell you about the calorimeter a little bit. So here's a photo of it. You can see this array of microscopic structures on top. It's a 3-inch wafer, 3-inch silicon wafer. There's an array of transition edge sensors on it. Each one of these shiny dots is a transition edge sensor with aluminum around the sensor. So this is just a single channel. It has a resolution of 2 and a bit eV sigma. That's a resolution for energy in the silicon. And then it has this phonon diffusion step in the silicon. So whenever you put a signal into the silicon, it takes some time for that signal to arrive in the TESs and some time for that phonon population to be fully absorbed. So it's roughly a 20 microsecond rise time and a 90 microsecond fall time. And I just want to emphasize this is all entirely athermal. So incident energy, an atom or a photon hits the silicon. It produces an athermal population of phonons in the silicon. They produce a thermal population of quasi-particles in the superconducting aluminum, which then diffuse into the transition edge sensor. So it's all athermal, and that makes it relatively fast compared to previous work looking at these things. Last technical note before we finally get into the data, ensuring that the sensor is dry requires tuning of the thermal mop. So here's the cell, here's the sensor platform, and that sensor platform is linked thermally to the rest of the cell, of course, through the walls of the cell. And it also needs to be linked to the mixing chamber. Remember that the sensor threshold goes roughly as the temperature cubed. So we want a thermal link that's pretty strong between the sensor and the mixing chamber to keep it cold. But after we fill the cell, we need to bake the sensor up to roughly 1 Kelvin temperature in order to get that last layer of helium-4 off. So that took a fair amount of tuning of everything. We minimized the thermal link between the sensor and the rest of the cell, especially the helium-4, because we don't want the helium-4 vapor pressure to increase when we bake the sensor. And we need to tune the thermal link between the sensor and the mixing chamber up here so that when we bake the sensor, it's isolated enough to get quite hot, but connected enough to get back down to sub 10 milliK temperatures afterwards. So anyway, just to emphasize, we've overcome some technical challenges successfully. So here's the bake temperature of the sensor. We're achieving more than 1 Kelvin temperatures on the sensor, which is great. And we're able to see the sensor signals for a known calibration line. And we can see that the more we bake, we increase that signal, and then we can prove that the sensor is dry. So just, again, maybe I'm just bragging about technical accomplishments, but this was a lot of work. Okay, so finally onto the data. So what do we expect to see? We expect to see 2 signals. First, the photon signal from the singlet decays that are all prompt. And then after that, the phonons and the rotons, the quasi-particles, have some propagation time. The helium atoms of the evaporation signal have some propagation time. So we expect scintillation followed by some delay time, followed by the evaporation. It's roughly 100 meter per second phonon velocity or roton velocity. And so if you have a centimeter scale target, you expect a delay of order 100 microseconds between these 2 signals. I've started calling them S1 and S2. That's a little bit of jargon, sorry. And then when we look at the data, it just feels, I don't know, every time I look at this plot, I get happy because it's just really nice to see all of these years of hard work on the hardware finally paying off. So we see prompt scintillation. This has the timescales of the sensor. So this is the silicon phonons rattling around. 20 microsecond rise, 90 microsecond fall, because it's just a delta function, one-time scintillation input. And then after some hundreds of microseconds delay, we see the evaporation pulses. And now, like I say, we can have a lot of fun now that we're at this point. So we place X-ray source at the bottom of the cell here. It has iron 55, which produces the 6 keV line, and we cover it with aluminum tape. The aluminum fluoresces, which produces a secondary X-ray line at 1.5 keV. And you can already see them here just in the raw pulse data. We see this strong peak at the 6 keV energy. And then here, closer to threshold, we see the evaporation pulse from the 1.5 keV. If you look at those signal amplitudes separately, so I've plotted scintillation on one axis and evaporation on the other. You can see a nice peak in that 2D space for the iron, and you can see this peak kind of straddling threshold for the aluminum. So over here, if you just kind of divide by 16 eV, you can get the equivalent rough number of detected UV photons on the scintillation side. So you can see we're kind of at the 10, 20, 30 scale here. That's the number of photons we're detecting in the scintillation signal. And our threshold is something like 2 photons, roughly. So these amplitudes and widths on the scintillation roughly match our expected, should say, singlet yield, and the solid angle for the photons. They roughly match, the width roughly matches some basic assumption of Poisson fluctuation on the production and binomial fluctuation on the detection. The evaporation, though, is our primary signal. So that's where my eyes will always be focused on what's going on with the evaporation. Maybe just to emphasize, the evaporation signal has a better energy resolution than the scintillation signal. You can think of it just as a square root of n effect on it. This is that same plane, but now we're varying the fill height of the helium. So you can see that for the smallest iron signals from the bottom of the cell, filling different fill levels doesn't really change the scintillation. You always get roughly this 260 eV. but the bottom of the detector for evaporation does change. So there's not that stable level. And you can see that's because there's this critical angle for evaporation, and there's this wide angular spread of the outgoing atoms. So the closer you get that liquid surface to the sensor, the more of the atoms you're collecting from the evaporation. So the solid angles work a little bit differently for the two different signals. We can plot distributions of the evaporation delay time. So this is, again, just how long did the quasi-particles take to get to the liquid surface, plus how long did the atoms take to get from the liquid surface to the sensor. So the longest times here are for the bottom of the cell, and you can see that as you fill the cell, the times get shorter and shorter because the atoms are just very slow. The atoms in the vacuum are something like 100 meters per second, and the quasi-particles in the helium are something like 200 meters per second. So we're kind of building a model to make sure that this distribution makes sense. Right? One of my key questions from a practical standpoint, trying to turn this into a detector, is can we get the rotons to reflect off solid surfaces? Can we get them to scatter many times and still evaporate? So you could assume very good reflection from a very naive model of how waves work at that material interface. You could assume no reflection if you look at the wavelength of the quasi-particles and see that it's very similar to the roughness scale, and maybe they have a very poor, maybe they have a very high transmission into the material. So to me, this reflection at the surface is one of the big, I'll say it, a big can of worms for this whole technology. We want that reflection to be high, and that'll be one of the main things I'm going to work on the next few years, is trying to make that reflection as high as possible through trial and error, essentially. But so let's look at the data and see, do we see any quasi-particle reflection? So the first thing you might do is just look at the pulse shapes and see, do you see echoes of quasi-particles bouncing off the bottom, reflecting off the walls, etc. So if you select pulses from the top or the middle or the bottom using that delay amplitude, delay timing, then you do start to see subtleties in the falling slope here, where you do see kind of differences between different positions that are likely a result of reflections. However, they're all smeared by this 100 microsecond silicon sensor timescale, so it's pretty hard to deconvolve the reflection physics out of this pulse shape. If you look at scintillation amplitude as a function of depth, so now I'm combining the amplitude and the delay time quantities. So here at the top, you see larger scintillation amplitude. At the bottom, you see a smaller scintillation amplitude. And that makes sense. We're just seeing a change in the effective solid angle of the sensor, right? So you're looking from the bottom of a well here at the bottom. If you do exactly the same study, though, for evaporation, it's very, very different. So at the top, your evaporation signal is smaller. And at the bottom, it's boosted by a significant amount of extra signal. So that was a surprise, at least to me. You might expect naively there will be very little change with depth. All of the evaporation might occur only from phonons within this solid angle. And so the depth, the effective solid angle of the sensor doesn't really play a role. It's just this constant solid angle of the critical angle region. It's something like 17 degrees. So my naive, I'll say, assumption going in was that we would see a fairly constant amplitude as a function of depth here. So the solution to this puzzle is to look at this indirect quasi-particle population. So quasi-particles that are incident on the metal, that population has, well, you can see kind of the solid angle of the metal as viewed from the recoil site is larger the deeper you are. At the top of the volume, you have something like a 2 pi solid angle. And at the bottom, it's greater than 2 pi. So these quasi-particles incident on the metal are kind of somehow responsible for that increase in the evaporation signal. They propagate away from the recoil site, and when they reach a metal surface, our hypothesis is that they are reflecting diffusively at a random angle, and they have some chance then of ending up within the critical angle to reach the liquid surface and cause evaporation. So again, the deeper you are, the larger this incident on metal indirect population is. And then if we make a very simple first order model of that process, so we assume the reflection is entirely diffuse at metal surfaces. We assume that it has a probability of about 0.3, which is consistent with others in literature, including Heron experiments. And for simplicity, this is just a first order thing. There's no double reflections going on. And then what we see is that that's consistent with what we see in the data. So we would have a direct quasi-particle evaporation population that doesn't depend on depth. And then you get some depth-dependent boost. If you have no double reflections, this is linear, surprisingly. And you get kind of a 20% boost near the top and a 40% boost near the bottom. So this is great news. It means we have a clear, easy to measure, observable for the reflection quantity that we really want to understand moving forward. We can vary things about the cell and see whether this reflection increases or decreases as we vary attributes of the cell walls. Okay, so if you look at the waveforms, but you deconvolve them, so you take the timescales of the sensor and deconvolve the waveform, you can get a plot that just shows you the power onto the silicon. So if you do that procedure, you can see essentially a delta function for the scintillation. After some time, you see a smeared region. So the evaporation is not occurring as a delta function. It's spread over some hundreds of microseconds. And then after that, you see this many small individual triplet quenches. So these appear as delta function inputs of power, and they occur only after the pulse, not before. Just to emphasize, this is 74 pulses, and we've deconvolved each one and stacked them on top of each other. So you would see about one of these triplets per aluminum event. And we have about 74 of these triplets in this stacked plot. So we have really interesting data in my mind now to try and understand some things about triplet physics. If you average together very many events, then you can get power as a function of time. And you see these timescales at tens of milliseconds after an event that are, we assume, are due to triplet quenches after long delay. There's a couple of features here. We see a shoulder at roughly 4 milliseconds. So first, I'll just start. This red curve is the pulse shape if you just directly input energy into the silicon. then you see in the helium events, there's this evaporation afterwards. And then at long time scales, we see these triplet behaviors. So we see the shoulder at 4 milliseconds, and then we see a decay that's roughly an exponential decay with the roughly 10 millisecond time scale. So I have a lot of questions here. This doesn't make a whole lot of sense to me yet. I'm kind of showing you our laundry a little bit. So I don't really understand this shoulder feature. I would naively say, well, this is related to the time scale of quasi-particles arriving at the metal surfaces. And the implied velocity works out. It's a few meters per second, which is consistent with the work of some others on this call. But then it doesn't really make sense when you look at Z dependence. Why would that shoulder have a higher rate for events at the top and a lower rate for events at the bottom? The solid angle argument from before would say that should be swapped. We should see more quenching on metal for events near the bottom. So something doesn't make sense there with my first guess. And then this long time scale, the 10 millisecond exponential, we really expected triplets quenching at the liquid surface to have a long time scale. It takes time for them to diffuse and find another triplet. But we really expected that to be a 1/T behavior. It should depend on the density of triplets on the liquid surface. And this is not a 1/T behavior. So there's some mysteries here. I'll just state them and you can think about them. Some things we're figuring out. Varying the cell will obviously give us a really strong handle on, what of this changes in what way when we vary the cell dimensions. But from a particle physics standpoint, this is all good news. These timescales are workable. They're not too long to ruin the experiment. The sensor has this, remember, 2 and some EV sigma resolution, which means that we're kind of just barely able to see individual triplet quenches. So here we're running a filter that translates pulse amplitude into EV. So you can see this bottom trace repeatedly has some peaks that are kind of around this 20 EV energy scale, and that's consistent for all of them. So if we make a histogram of peak amplitudes, you can see that there's this bump a little bit below 20 EV, kind of right where we expect it. We're not making any great claims here on measuring that energy, just that we're looking forward to understanding the energy of the triplet quenches in the future. Hopefully that'll tell us whether we're seeing things on the metal or the liquid surface more distinct. I think this is the last thing from the data that I wanted to show. So we've exposed the helium to both nuclear recoil and electron recoil sources of radiation. So neutrons, which to the atom, versus an electron recoil from a gamma, which excites the electrons. So we expect widely different ratios between these atomic signals and the quasi-particle signals. And we see roughly what we expect. So when you use a neutron source, you greatly boost the evaporation or the quasi-particle signal. And you also significantly boost the triplets at late times, at least when you're at high energies, that's true. So this is just very rough so far. Let's see. I think I'm going over, but I think I just have 2 or 3 slides. So now that we've reached this goal, what are our next few steps? Really, as I emphasized at the beginning, the primary goal here is to push the threshold as low as we can. So what can we do to push that threshold low? One is to increase this gain mechanism. How many milli-EV do you get per atom? what is the van der Waals potential or the van der Waals attraction between the helium atom and the calorimeter surface. So looking through the literature, it looks like some people have done some computational studies. They've predicted that van der Waals potential for helium on sapphire, and they found that it's 20 to 30 millieV per atom. So that's a factor of 2 or 3 better than we think we're doing right now. So we're already starting to fabricate sapphire-based detectors, and we're going to test those soon and compare the signal amplitudes between the sapphire and the silicon calorimeters, and hopefully see 3 times better performance. So that'll be an interesting study. And then back to this reflection, I think that this is just a really complicated interface between the helium and the solid. So there's surface roughness, there's van der Waals, kind of a pressure being applied to the helium, which changes the dispersion relation in that very near region. We see something consistent with roughly 30% reflection at that interface. So then the question is obviously, what happens to the other 70%? Is it transmitted into the material? Is it broken, kind of down converted into multiple lower energy quasi-particles? So there's a medium-term plan in my group. We want to vary this interface. We want to vary the surface between the helium and the bucket. If we boost that 30% to 90%, or optimistically 99%, that would dramatically reduce the threshold and dramatically enhance the sensitivity of the experiment. So I'm looking for ideas of things to try on that base to boost our reflection probability. All right, so yeah, that's my talk. Thanks. There weren't very many questions. Hopefully you'll have some questions now. We've successfully demonstrated a lot of things: the heat-free stopping of the helium-4, the scintillation and evaporation readout at this limit really close to the threshold of evaporation. We're seeing few photon events. We see triplet quenching on 10 millisecond timescales and not longer, which is really important demonstration for the experiment. And maybe I should explain this number for a minute. The phonon overall efficiency and gain is 0.15. So for every EV of energy that you put into the helium, you see 0.15 EV in the silicon. So this is a combination of the evaporation efficiency, the reflection efficiency, that gain factor onto the calorimeter surface. All those things folded together gives this overall scale factor. And then we have some ideas of things to do next. So I think this is a pretty interesting topic for condensed matter people. I'm always looking for people coming from condensed matter to join my group, grad students or postdocs. So get in touch if you want to make that transition, and I'll stop talking. Thanks.
Thank you very much. That was really interesting. I have some questions, but I think Dima should probably go first.
Great.
Right. Yeah. Thanks a lot, Scott, for the very interesting talk, and congratulations on the experiments. They look really promising. So yeah, I wanted to.
Stuff I know it's highly relevant to you. And
yeah. Well. I wanted to first ask you about the impurities, helium-3 impurities in your helium-4. So do you know the limit?
So we are not the ones purifying it. So we get it from, now I'm blanking on his name. We get it from Manchester, right? Or
yeah, probably from Lancaster, from
Lancaster. Yeah, I'm sorry, I don't know my UK geography.
All right, fair enough. Yeah, that should be quite pure.
So other people have tested that, and I know there's some debate between people about what the purity is. all I can say is that we believe it's well pure enough to have ballistic length scales at the centimeter distances that we're working with.
Yeah, so, well, I've worked with Ximers in helium-4 for a bit, and then so for some reason, I'm not sure we know why, if you add really tiny amounts of helium-3, then the Ximers are quenched very quickly, so a lot at lower temperatures, a lot faster than 13 seconds. And I think something similar could be happening in your experiment as well. So the thing is that helium-3 atoms tend to be adsorbed at the surface or free surface of helium-4 and form so-called Andreev states. So they're not Andreev bound states, which is kind of a very popular topic now, but they're called Andreev states. And so in kind of my intuition is that any tiny amount of helium-3 that you have will get adsorbed on the free surface, and that's where you think your Ximers are. And yeah, for some reason, helium-3 might shorten this lifetime. So that's my comment.
That would make a lot of sense if it was, especially on the liquid surface, we would kind of have a consistent in time number of sites where decay can occur.
Yeah.
And so follow an exponential based on the density of the helium-3 rather than on the density of the triplets on the liquid surface.
Yeah, so that would be my guess, but I'm sure many people will
That makes a lot
more.
of sense now that you say it.
Yeah, thanks. And good luck.
Thank you. Thanks.
All right, thanks, Dima. I think Henri Godfran is the next one. Please go ahead.
Okay, hello, can you hear me?
Yes, loud and clear.
Okay. Yes, I was interested in these collisions between the roton and the surfaces, and this is very similar to the collisions between the neutron and the surfaces that we investigate. And I was asking myself that you should see some directional effect. I mean, if you do some kind of grazing incidence or a perpendicular incidence, it could be different. Of course, it's a little bit tricky, the system, but that's my first question. And the second question is, did you contact people who like Eckhard Krawczyk, who can calculate the collision between a helium wave and a helium surface?
So let me make sure I take your two questions and give them each their due. So the first question, when you say directionality, do you mean directionality of the incident quasi-particle or of the atom that's recoiling?
What is reaching the surface?
Mm-hmm. So yeah, my picture is the recoiling atom produces a hot spot of quasi-particles, and it loses all of its directionality from the recoiling atom quite quickly.
Okay, sorry, I'm talking about what happens inside the liquid and the rotons hitting the surfaces.
Right. So then I agree there's significant angular dependence at all the interfaces, and that it can get very complicated very quickly. And what we have is essentially a very simple model. And we'll be very interested to look for differences between this, what can we see in the data? And I think we haven't seen anything interesting yet. It's all consistent with a very simple model so far. We don't have any radial information because we just have a single channel.
Mm-hmm.
So we only have one-dimensional position information. And yeah, I think it's hard to parse out that kind of subtlety so far. But yes, it'll be very interesting to look for grazing incidents. Maybe reflection is very easy at grazing incidents.
You talk to theorists about that, people like Krawczyk?
So I've looked at papers and I've seen a wide variety of opinions and wide variety of models for the quasi-particle interactions with these surfaces. In my mind, this surface is a very complicated region, and it feels like kind of the experimentalist regime rather than the theorist regime. Like it's very
Well,
difficult.
both. It's a combination of both because you don't have too many excitations. What you are interested in is the couple of liquid layers which have a slightly different density and which are on the solid layers of the surface. So that is slightly different from the bulk and will make some and has some, as you said, many excitations which look like the bulk ones, but they are shifted in energy and momentum.
Right.
So
Right.
okay, that was
Yeah, I mean, if I have looked at papers, and it does seem like there's a wide variety of opinion. If you send me a link to a paper that you like, I will definitely read it. Absolutely.
Yeah, well, I think it could be more to know if one can do a calculation to see if there is some orientational effect that is marked enough so that you can use it. But okay.
Yeah. I guess maybe one thing I'll highlight is that the solid surface just by itself is usually fairly poorly understood. Kind of, is there any oxide or not? What is the lattice structure in the outermost few atoms?
But how do you clean these surfaces? Because if you don't really clean it very thoroughly, you have air always on all these things.
Right. So we attach a turbo pump to the cell at room temperature, but we don't bake the cell.
No, then you have air. I mean, the surfaces will be more or less always the same.
Right.
Yeah.
So the one thing that helps us is the cesium itself acts as a gettering material at some level.
But it will not remove all
the cesium doesn't exist until we're below 100 Kelvin. So there's some suspicion maybe it's not gettering at all because we're too cold.
Unless you use graphite surfaces, you will always have some air on top of the metal.
Yeah, so I believe we do have some air, and baking better is something to look into for future. Also, I'm interested in just depositing cesium on the walls of the cell too. Maybe that reflection at a cesium interface would be very interesting.
Thank you.
Maybe. Yeah. Thank you.
All right, Marvin is the next one.
Yeah, I just had a quick one. Thanks for the great talk. You said you're not worried by the background of thermal phonons in your thermal bath, basically, because you're below 100 milli-K. What about the phonons in bulk acoustic or surface acoustic wave modes that are excited through vibrations from the fridge that you could have from pumps, for example? Would they constitute a background?
Yes, so they would constitute a background. That's something I'm, on the lookout for. What is our constant baseline rate of evaporation, and where is it coming from? I'll say that, we do see a high rate of scintillation and evaporation, and kind of, I would, just random. There's a lot more happening at 10 EV once the helium is in the cell than without the helium in the cell. And so pulling apart that much higher rate and understanding it is really important. And it might very well be that vibration is a huge challenge to this. And that's something to understand. There are ways to mitigate it. We can suspend the cell. People have had success doing that in other dark matter experiments with some vibration decoupling setup. I'd like to avoid it. Let's see.
Thanks.
All right, Wei is the next one.
Scott, very interesting talk. I like the result very much. I should have attended more of your group meeting talk. I have a naive question. So when you push the limit to detect few EV event or even sub EV event, you only have the evaporation signal.
Yeah.
In this case, how could you distinguish between nuclear recoil event and electron recoil event?
So I have a couple answers to that. First, I'm very excited to be in that regime. Once we're into that regime, a higher fraction of our recoil energy goes into quasiparticles, right? So once you're below 20 eV, 100% of your recoil energy goes into quasiparticles. So this is a tipping point where your main signal, the one that has the gain mechanism on it, becomes your only signal and much more efficient. There's no triplet backgrounds. In my mind, when you have energy go into the singlets, it's not that useful. I really love the quasiparticle energy as the primary signal. So whenever you see a quasiparticle signal from a sub 20 EV event, then you know that you have good energy resolution, and you know that it's a nuclear recoil, because there is no such thing as an electron recoil below 20 EV. There's no way to excite an electron to 10 EV in a ground state helium atom. So that's actually something really powerful about helium atoms, is that their first excited state is a really large energy input to get to it. So it makes it impossible to have an electron recoil at low energies. We have this window for a dark matter search where our backgrounds are dramatically suppressed. Gammas cannot put 10 EV of energy into our target. It's not physically possible.
So essentially, you are looking for events only with S2, but with no S1.
Yes, and then that's why we need to move to a multiple channel readout, like in this cartoon.
I see. Got
We
it.
distinguish evaporation events from backgrounds in the calorimeters, because evaporation events appear in more than one calorimeter.
Got it. Thank you very much.
Yeah, so we actually have this device in lab right now, and this will be our next run. We've just cut the circular calorimeter in two. So we'll have 2 calorimeters next run, and it'll be very exciting to see what do these low energy signals look like, including, to the previous question, what do things at 10 EV look like when you have 2 channels looking at them? That might be an important way to suppress low energy backgrounds.
Yeah.
Is there a fundamental limit to the threshold you can reach in the system?
The ultimate threshold is the single atom being evaporated. So roughly the 1 million recoil energy.
Yeah.
That's, I'd say, decades away. We won't get there anytime.
Rob?
Hi, Scott. Yeah, I just wondered whether it's important for you to find a mono-energetic calibration source down at these like really, really low energies.
Right. So right now, I'd say we're somewhat safe from the calibration question. And that's because the model is we have this recoiling atom. It makes kind of a hot spot in the helium-4 that is thermalized. And then the quasiparticles stream out from that hot spot. So every recoil should have kind of a certain volume and a corresponding temperature to that hotspot volume. This seems like something that, well, I guess there was a paper that modeled this effect, and it's a fairly weak energy dependence on the quasiparticle, like the momentum distribution of the free streaming quasiparticles coming out of that hotspot. So I'll say we don't expect a strong energy dependence in these signals until we get to the energies where it's no longer a thermalized hotspot of quasiparticles. So at some point we'll get to an athermal regime, where instead of a hotspot, we just have an atom producing a handful of quasiparticles that then free stream out without that thermalizing stuff. I think that's pretty far from now. But at the same time, I have a grad student whose full-time PhD career has been spent developing a 2 keV neutron source for our lab. so that we can test nuclear recoil response at 1 eV, 10 eV scales. So yeah, I don't mean to diminish your question too much, because I do have people working on it, but I don't think it's a showstopper, at least not for some years.
Okay, great, thanks. Great data as well, by the way.
Thank you. I'm very happy to share it. I'll be honest, it feels really good.
I'm not seeing any other questions at this time. So I think it's time to thank Scott for this very interesting talk today.
I should have included my email in my slides. I hope that people should feel free to reach out to me by email. I'm interested in any later questions. If you think of something in the shower, get in touch.
All right, thank you very much. And this talk will appear on YouTube when I get it processed. And the next webinar in the series will be advertised on the email list. Well, when we have sorted out who happens to be the next speaker. And that's probably all I wanted to say. So thanks everybody for coming today, and see you next time.
Thank you all. Appreciate your time.
Thanks. Bye.